Okay, hello everyone. So this will be a continuation video on differentiation. The topics that will be discussed in this video require understanding of the basics from the previous differentiation video, which is the basics that you would see in normal math extended. Right, so I would request any viewers viewing this to first view and understand the previous video, and I'll be sharing the link in the comment section below for that one. Okay, alright, so I'm going to begin by discussing a little proof that I decided to skip a bit on actually for the previous video. It's the first principles. It's the first principles for differentiation using the limit idea, right? So this was something that a lot of viewers, especially A-Math students, requested. So I've decided that I'm going to begin by discussing a general proof for this, and basically what we're going to show is that we want to show the derivative of x power n is n times x power n minus 1. So basically this is a proof, a general proof for the power rule from first principles. This is something that you don't really need to know. For normal math, it's way advanced, because there are some techniques that you will need to understand from additional maths. For additional math students, this is something that I believe you would want to understand a bit more on. Right, so basically, like I've already discussed in the previous video, the formula is, of course, the limit as h goes to 0 of fx plus h minus f of x over h. Well, if we immediately decide to plug 0 into that, everyone knows something divided by 0 is undefined. Right, so we're going to have to be a bit smarter in how we approach this. Right. Well, if you notice, we know that f of x is itself x power n. Yep. So we know f of x is x power n, which means if you have studied your functions properly, then you will know that fx of h is x plus h power n. Yep. And this is what I mean by this proof needs some stuff from additional maths. Well, how do you expand this? Well, the binomial theorem states that the expansion of a plus b gives you this expression. Right? This is something that I will say to be assumed knowledge for you guys at this point, because I will have presumed that all of the people studying differentiation have already studied previously series AP-GP binomial theorem. So in other words, this is something all of you should know. Anyway, yes, so if we continue all of this, right, and this goes on until you only have n, well, the last term is n, h power n, right? So now we know that, yeah, this is the expansion of f of x plus h, and we would want to subtract this by x power n, and we're going to divide everything by h, right? X power n cancels out. Okay, so x power n cancelled out. And now if we evaluate this, well, n0 is just what? N factorial over n right. Yes, so this is NCR, right? So this is n factorial over sorry, this is n1, this is n1, this is n0. N0 is n factorial over n minus 0 factorial, which is factorial, so that's gone, right? Which means that cancels out. This is 1, this is 2, all the way until n. N1, right? The binomial term here would be n minus 1 factorial times 1 factorial, right? Times x power n minus 1. Well, h and h cancel out, right? Yeah. So essentially we can rewrite everything here as factorial times 1, because h and h has cancelled out, times h power 1, because h squared and h cancel out to make h, and this goes on until n factorial over n factorial, right? This is and that's all gone, right? So this is n minus 1, right? And this would give n factorial over n minus 1 factorial, right? Yeah. N minus 1, which gives 1 factorial, which really that just cancels out, times h power n minus 1. Do we have to evaluate any of these? No, because we're trying to find the limit as h goes to 0. And what that means is that at h equals 0, this is 0, this is 0, all of this is 0. This is the only term that you need to think about. N factorial over n minus 1 factorial, that's n. X power x minus 1. which means that all HS equal RHS. And prove it. Right. Moving on. I'll now discuss some slightly more advanced rules. Right. So previously we have discussed how to do constant multiples. Like if you have 3x squared, then this is just 3 times the differentiation of x squared. Right. If we have the differentiation of a plus b, where a and b are both functions of x, then it's just the derivative of a. You first find the derivative of a, and then you add that with the derivative of b. And again, in A math, right, this is basically just saying the derivative. Why is there no y? Because this right here is your y. d dx times y is dy dx. As far as I'm certain, and as far as everyone here is certain. Right. Before we move on, I'd like to explain a bit more that I say this is a function f of x. Another way to write the derivative is using the prime notation. So this is the same thing as saying dy dx. And this is the same thing as saying an f double prime is the same thing as the second derivative that we discussed last time, b squared y over bx squared, which really, sorry for interruption, which really is just d dx, the derivative of d dx of y. So these are all actually just the same thing. These are actually just two different notations for the derivative. There, right? So this is what's called. So that is called Leibniz notation, and this is what's called Lagrange notation. In the exam, all you have to know is that both of these are just the same. So if they ask for f prime of x and if they ask for dy dx, it's exactly the same thing. And we all know that we can replace y with a function with the explicit function y equals 2, right? And then we can also replace y with f of x. So, in other words, this is a perfectly fine way to write down the notation for derivative. Okay, terminology aside. Now, right. Okay, so rule number 1. This is about the composite function. Function inside a function. Right. So I'm going to begin with a function f of x. Say f of x is 2x squared. And then we have g of x. Say g of x is x plus 3. Well, the composite function fg of x is of course 2 times x plus 3 squared. Again, for A math students, I will assume this as assumed knowledge, right? Note that to differentiate this, you could just open everything up. But this becomes a problem if you have to do the binomial expansion of something very complicated. In this case, say 7x, say 7x plus 1 power, let's say 1000. Well, you can't expect to do a binomial expansion of this number. Number one, of course, this. Number one, expanding this manually would be super error prone. Number two, this would be very bad because it would take you literally forever to do this. Well, nowadays we have calculators, so nowadays we have calculators, so really this is not very hard to do with a calculator. But then again, in Cambridge you're not allowed to use calculators, you're not allowed to use computers in paper 1, right? So you can't do this by hand, it's impossible. The way you do this is actually using the simple idea that we can split a composite function into its constituent parts by saying the inner function, right? The innermost function is u and the outer, and then we can differentiate that, and then we can differentiate the whole thing in terms of dy du, and then also in terms of du dx. What I mean by u here is this thing. Yeah. So this whole thing is y equal, right? Yeah. Okay, so now what happens if we let that become u? So now we have the expression 7 power 1000. And that gives you, this is very basic power rule, 700,000 times u to the power 999. Right, here's the thing, right, this is your u. Right. So now we have u equal to x plus 1. You find du, you differentiate in both sides, so you get that du dx is 1, and then you just multiply 1 with this. Don't forget, you have to sub this back in, and this is your final answer. This is if the inside function is x plus 1, that's easy. If we add a coefficient or something, then you will have to multiply. Then this is not 1 anymore, this is 3. So you multiply this by 3. So this is not 7,000, this is 21,000. Okay, from here, you can probably already think that there's actually a similar algorithm for chain rule. Yes, this type of algorithm where you turn the inner function into a different variable as a parameter, and then you differentiate that inside and then apply it with the outside, is chain rule, because everything is in a chain. Like here you have dy dx, dy du du dx. Right? This is interconnected. This is why we call this chain rule, in a sense. Okay, so how do you find an algorithm for doing chain rule without having to do the very long formal way of substituting it and whatnot, right? Right. Let's go back to our 7 times 3x plus 1 power 1000. Right. If you can work this out in your head, right, this would essentially just be for this kind of stuff, you drop the power, turn this -1, and you times by the differentiation inside. Okay. Right. So now what if you have something like this? Well, and now what if you have something like this? This is just, don't be scared, don't be fooled. This is just actually this, indices and surds. Like, again, this is just basic indices and surds. How do you do this? Well, you drop the power, and then this becomes 2x plus 1 half minus 1, right? So you get minus half. If this was x, by the way, this would have been very easy. Half times x power minus half, right? And then this is going to be times by the differentiation of the inside. So that's gone. And then based on your indices and surds knowledge, you should know that this is your final answer. Okay. Right. So now that I have discussed how to do chain rule involving surds, now let's make this a bit more challenging. Two x minus 1 plus 3 power 2. Okay, so again, this works exactly you would want to, right? So essentially what you do is that this is the outermost function. All right, think of it as the idea here is like the Matryoshka doll. If you've ever seen that, then you will know how this works. So this is your outermost function. This is your second function. Right. Well, no, because 7 is just a constant multiple, so you can just leave that out. This is your outermost function. Right. Then what's inside? This is your second layer. What's inside is surd. Right. Which means that you just have to think of this whole thing as a single variable. So basically how you could do this is by thinking everything as a single variable, and then you multiply it by the differentiation of the inside variable, right? The tree is gone. That becomes half of 2x minus 1 power minus half and then what's inside that? You differentiate the inside of the, this is the innermost function, 2, and then you can simplify everything. And your final answer for this, and basically you can generalize this for any number of functions that you need. So basically I can generalize this for doing the chain rule of 1, 2, 3, or maybe even more functions if they ask you for it. So this is kind of quick trick. So you differentiate the outermost function, think of the inside as a parameter, and differentiate that parameter, and then if there's something else inside, think of that as a parameter and then differentiate that until there are no more inner functions, inner rooms to go to, as I like to call it. Right. For AMAF, you will have to know also, other than the differentiation of composite functions, you have to know the differentiation of products and division of two functions, quotient of two functions. You can also call it that. This is called the product rule. By the way, this is called the quotient rule. For this, basically your U and your V are in terms of X. Yep. Well, they can be any power except other than power of 0, of course, because if U is in the form 2x, say this is 2x power 0 times 3x power 3. Notice that this is just 1, so this whole thing evaluates to 6x power 3, and this is a basic example of constant multiples, right? What I discussed earlier, right? So basically, in other words, this has to be a function of x of power that is not 0. Same thing for this. Okay. Right, I'm going to take a little simple example. Right, let's take this function. Well, you can always expand it and do simple power rule. Right? Power rule, addition, subtraction, constant multiples. Right. The other way of doing it is to remember that it's use the product rule formula. Just for products, it's U prime V plus UV prime. Or sometimes you'll see this as V du dx plus U dV dx. Yep. Oh, right. Well, this is something that you'll have to memorize because they're not going to give you the formulas for calculus in AMAF. Yep. Right. In this example right here, well, U prime, let's say this is our U and say this is our V. U prime is 2, V is just simply x minus 4, just bring it down. Yeah, and then our U now is 2x and our V is 1. and by opening all the brackets and everything, you will get that. It's 4x minus 8. And this is 2x squared minus 8x, right? It matches, right? Okay, so, and then for quotients, it's u prime v minus uv prime. U prime v minus uv prime, right? Actually, this can be. Actually, we can derive this actually from the product rule of u times 1 over v. Well, u and v are functions of x, right? Yeah. Right. U prime, so basically this is exactly the same as saying f prime of x, except you don't write that x because essentially this is shorthand. Essentially this is shorthand notation. Yeah. So this and this basically mean the same thing, by the way. It's exactly just like how this u prime thing works. Back to this. So u prime times 1. U prime over v minus uv prime, over v squared. And you can actually derive this because this is u, right? U prime 1 over v, right? The differentiation of that, say v is, yeah, then isn't that just v? 1 over v is actually just what? If you think about v power minus 1 minus drops down minus 1 minus 2, which means u prime over minus v squared. Yes. Minus what? What's the other one? This is your v, right? Yeah. Okay, plus. This is our v, right? Yeah. Times what? Times u. Right, this is our uv prime. Sorry, u prime v, right? U prime over v, right? U, right? Right, this is plus, right? U over minus v squared. Yeah. And this is your, right, so it's u prime v, and then this is your, right? Yeah. Or u prime over v plus u over, right, this is your v squared, right? Since this is a function dy dv times dv dx, right? Yes, this is your dv dx. dy dv is v prime. And so really, right, if we think about it, this is just u prime v. Yes, this is just u prime v over v squared minus uv prime over v squared, which gives us this formula. Okay, now I'm going to show example for quotient rule. Find the derivative. Well, how do you do this? Well, u prime v minus uv prime over what's at the bottom, and this gives you 6 over, and this is your final answer. Okay, for A math level, there's going to be one additional application of differentiation that you'll have to know. Well, of course, with tangent lines, turning points, they're going to make you find the tangents and stationary points of curves with, guessed it, with chain rule, quotient rule, product rule put inside here. The other application, chord geometry wise, on an xy coordinate, is that you will have to know is basically, in a way, this is a further application of the tangent line to a curve. So this is our tangent. The normal line is the line perpendicular. So these two lines have a perpendicular gradient, and they both intersect at the point where the line is tangent to the curve, at the point of tangency. So basically, the way you find this is basically just find the line perpendicular to the tangent line at the point where the tangent line is tangent to the curve. So, alright, so we know our perpendicular gradient is this, right? If the original gradient of the tangent line is m, and then say the coordinates of this point is a comma b, then you substitute a over here, b over here, and you will get your c, and you already know your m from your derivative, right? From doing the reciprocal of the output of the value of your derivative at that point. And so you can then find the equation of the normal line. Also in A math, oftentimes they will not only ask you to find the equation of the tangent or normal line, but often they will also ask you to find the intersection point or points of these lines for the curve. Again, this is just another application of simultaneous equations. Non-linear simultaneous equations. One of the two equations is linear, of course, the line. The other one is the curve. Right. To end this session, I would like to remind everyone that in these types of questions, right, if you know how to find your derivative using power rule, chain rule, product rule, quotient rule, if you know how to solve simultaneous equations if needed, if you know how to set your dy dx to 0 and then solve for your dy or for your x, for additional maths, you will be safe. All you need to know other than this are the specific differentiation rules for the other types of functions: e power x, ln, sin, cos, tan, that you will have to memorize. And basically questions about those will often just be: find the equation of the tangent line, find the equation of the normal line, find the equation of the stationary point, but using different functions. So if you know all of your calculus formulae, then you should be able to understand and know how additional maths, how differential calculus for the most part works. Yep. And for now, I'm going to leave it at this point. Yep. For next time, I'm going to discuss a bit more on differentiation, a bit closer to the AMAF exam, presumably, on rate of change, small changes, and then how you can apply this problems with the second derivative to the real world with practical optimization, and how we are going to discuss how the derivatives of functions which are not algebraic functions of x, and we will discuss how that's going to work. Right. Thank you for listening, everyone. Yep. And I hope that this will be beneficial to all of you. And I wish all of you the best of luck for all of your remaining IGCSEs and IGCSE maths. Yep, don't forget that paper 4 for maths is in 5 days. So don't forget to study, and also don't forget to study for your additional maths. Good luck for your IGCSEs, everyone.